Hi everyone, welcome to the third Seismic Academy run by the University of Toronto Seismic Design Team. Today we're going to go through a quick run through of the competition rules and how we calculate the final annual building income, which is kind of what our overall score is based on. So just a couple of ground rules. Most of you have been here before, but if you have any questions, type them into the chat. A moderator will read them and decide if it can wait until the end or if it's important enough to interrupt me. The presentation, both the recording and the slides, are going to be saved to OneDrive and posted to our website. Please mute yourself because we don't want any random noise in the recording. And this lesson is based on the 2020 rules. So when the 2021 rules come out next year, it might be slightly different, but most things are going to stay the same. A little bit about myself. I'm a fourth-year civil engineering student at the University of Toronto. This is my fifth year on the team, including a year of co-op. I was the team captain last year, and I've been lucky enough to have been part of the previous 4 competitions. Okay, so a brief overview of what we're going to look at. We're going to look at, an overview of the competition. We're going to look at what the SLC provides to us, the SLC being the Student Leadership Council, the people that run the competition. We're going to run through the rules, and then we're going to look at how to calculate your score on Excel. I recommend that you have the rules open and you kind of scroll through as we go through them. I put the link in the chat for both the competition website for last year and for the rules for last year. So you can open those and have those along while we go through this. All right, so the Seismic Design Competition. A quick overview. So we build a 1.5 meter tall, 0.5 kilogram balsa wood tower. We install 7.7 kilograms of weights, which come as rods that go through the tower, and then we test them on a shake table on specific ground motions that we're given. Some of the main constraints are weight, so the maximum weight of everything, including any damping devices, the roof plate, and the base plate, can exceed 2.25 kilograms. We're constrained by the floor plans, which I give ahead of time, which you can see on the top right for last year. So you can see we had an L-shaped floor plan from 1 to 5 floors, and then the square from floor 6 to 19. That just tells you what you can build within. So you can build smaller than that, but no bigger. You're constrained by things like minimum and maximum member sizes, maximum member length, and what's called a fang surface, which is just a really complicated way to say where 2 surfaces are glued together. And we'll see pictures of that later to make it more understandable. There's also bonuses and awards. So there's the communication award, which is based on your proposal, presentation, and poster. There's award for architecture. There's a bonus for your prediction score, which is based on your predicted performance versus your actual performance. There's also an award for your best seismic performance, t-shirt design, structural innovation, spirit award, which teams vote on. But yeah, so what did they give you on the website? So if you go on the website, slc.eeri.org, you'll see the official rules, which are usually released around November. You'll have a glossary of terms, some clarification, so teams can ask questions using a form, and they'll usually answer within a week or 2. They release the ground motions, which sometimes they're released in October, sometimes they're released all the way in December, kind of no set schedule given. There's a design guide, which is a nice and easy explanation of most of the rules with a lot of pictures. Almost all the pictures you'll see in this presentation are coming from that design guide. And they also have some resources that you'll need for the proposal, including a shear wave velocity profile and a boring log, which are just 2 geotechnical reports that you get in real life that they give you that you can write about a little in the proposal. There's also some forms. So there's an SDC interest form, which is just for team captains to fill out to show that the team is interested. You have to register once you actually get into the competition to join. There's a clarification submission form, and then there are your performance predictions, which is where you submit ahead of time what roof acceleration you think you're going to get and what roof displacement you think you're going to get for both ground motions, as well as your floor area calculations. Because how it works is you tell them what your floor areas are for each floor, and then they just use a ruler to verify that. They also have all the rubrics, so for your proposal, your presentation, your poster, and for architecture. And they kind of just look like this for each one. Highly recommended to read through them when you're doing those various things, because they'll literally just read the rubric and give you a mark based on that. And you can see here why they gave you those 2 geotechnical reports, because part of the proposal is a geotechnical / site description. There are also some other documents. There's miscellaneous ones like the EERI and SLC logo, some shipping information. There's a list of important dates at the very bottom. Mailers, which are like more detailed information about the competition. Like they'll tell you where exactly it is and what each day is going to be like, things like that. And then also there's some relevant competition submission forms, like the Calcutta auction slide, presentation slides, a poster which you have to submit as a PDF, and your predictions. So that was just a quick overview. Let's go through the official rules kind of briefly. So scroll along with me as we go. I'm going to go in order that the official rules go. I'm not going to cover everything. There's a lot that you can kind of read on your own, or we haven't found to be as relevant, or it's kind of obvious, but also it would just take too long to go through every single thing in detail. So you can see in order what we have in the rules. The most important is the structural model section. That's kind of where a lot of violations happen. And you'll note in a lot of these places, I'm going to say something like, for this, you're going to get 3V or 5V. You'll see when we do the calculation of our score, V is just short form for violation. And essentially each violation, you lose $1,500 off your score. Your score is typically in the hundreds of thousands. So getting, 1 or 2V isn't that much, but getting 100 or 200V is, you're not going to place particularly high if you do that. So scrolling through in the introduction, we see that we have some competition objectives, which they just say like, what's this competition for? It's to promote the study of earthquake engineering, so on. We have a problem statement, which gives you more detail about that year's specific competition. It's mostly for the proposal, and it tells you, San Diego is located on a coastal plain between the Pacific Ocean and so on and so on. And also just gives a brief overview of the competition in its most brief form. You have a section about eligibility and registration, which just tells you how you can be eligible for the competition. And it just says, please submit a proposal, so on. You have to meet all the eligibility requirements and so on. There's a section on units, which is funny because it just says everything is in English units, inches, and pounds. And then what's really nice that they do is they give you a summary of notable rule changes. So you can see from 2019 to 2020, they changed the maximum floor dimensions, they changed the maximum floor area, they changed the revenue per port floor, and so on. So this is really helpful so that you don't have to go through, this year's competition rules last year and see what changed. Okay. Scoring, as I said, I'm going to go through later in more detail, but one thing we can go through now is just the bonuses. So you might think, what's the point of doing the proposal, presentation, poster, so on? The big thing is they give you bonuses, and these bonuses kind of dictate what order the top couple teams are going to come in. The difference between getting, first in proposal and presentation and having a 30% bonus is like the difference between probably being, first or fourth or something like that. These bonuses are really what make or break the top teams, especially the revenue bonuses. So you can see kind of what rank you need to get which bonus. Architecture, it might seem like it's not that important because it's only 8%, but really architecture also plays a role in the proposal, the presentation, and the poster. They all have kind of in the rubric, they'll all say like some part of architecture. So it's a little deceptive. If you have, a really good render, it's more than just this 8%. It'll show up in these categories as well, and vice versa. One thing to note is as we'll explain later, these all factor into just your revenue. Your analysis prediction score, which is based on how close your predictions for your displacement and acceleration were to the actual, only is just kind of discounts your seismic score. And we'll see later, this doesn't matter nearly as much. So like getting first place here is kind of equivalent to getting 1 or 2% in bonuses here. So, okay. And then, so as I said, we'll go through scoring later. I already kind of went through number 3 competition awards. So now I'm going to number 4. I'm not going through the design proposal because it's going to change every year. It's basically just a written proposal that you make detailing your tower design and then some of the geotechnical stuff, the title page. But you can get more into that later if anyone has some questions. Damping devices. So this is a little important for U of T because, we're always kind of interested in this. There's a couple of key points. So for every damping device, you have to submit a proposal and it has to be approved. So for our damping device that we used in 2019 Vancouver, we submitted a proposal and then we had kind of a back and forth for a couple of weeks where they wanted some things changed or both either in the proposal or in the actual design before it got approved. The damping device that you submit has to match exactly what you're going to do. So you can't, be sneaky and change something a little. and hope they don't notice, because if they do, you might get disqualified. And this is referring both to the device and also the location where you said you'd put it. You can use any material you want, although obviously any kind of weight restrictions still apply. So if you use steel, you're going to end up with a heavy tower. You're not allowed to have any base or floor isolation, which is when the response of your tower or of a floor above is separated from the response below. So if you have like rollers, like if you imagine a skateboard halfway through your tower, the bottom part's going to shake back and forth, and the top part's going to mostly stand still. The primary idea behind them is to dissipate energy, and I think the idea behind this rule is so people don't just use like basswood instead of balsa wood, call it a damper, but really it's just so your tower is stronger. And then also it has to be stable and fixed to the base plate if the damper is removed. So if your damper is a whole floor in the tower, you can't say it's stable and fixed if you were to remove that damper. They're not going to test this by removing it. I think that's mostly just a visual thing. But it should be pretty obvious. Number 5, structural model. So this section's kind of big, but also pretty important because that's kind of the bulk of the competition, and also often where a lot of violations come in for teams. So what is the structural model? It's the balsa wood structure, so including any frame, wall members, and gusset plates, which I'll get into, that are attached to the base plate, which is at the bottom of the tower, and the roof plate on top, as well as any damping devices. It also needs floor labels at every floor, which is just a little piece of paper that says like floor 1, 2, 3, 4, 5, and your school name on top. It can only be made of balsa wood other than any kind of damping devices. So, you can't use basswood or anything like that. But you can use any kind of glue you want. So University of Toronto often uses contact cement, but also sometimes super glue. You can also use wood glue, epoxy, chemical anchor, Elmer's glue. There was one team that 2 years in a row used hot glue, which was really interesting, but not recommended. All right, so for the next couple bit, we're just going to go through the rules. It's going to be a little boring, but just going to be pictures to help us along. So what are frame members and wall members? Frame members are kind of those thin sticks that you see in pictures of our tower. These rules apply for both structural and architectural pieces. So even if we don't think it's load bearing, this rule still applies. It has to be no bigger than 0.2 inches by 0.2 inches by 15 inches, but no dimension smaller than 0.09 inches. So even if you were to notch that member to make a connection work better, that no dimension can be smaller than that 0.09. They give you a tolerance. So if they actually measure this, that's what their tolerance is going to be. So it's actually, it must fit in a 0.21 by 0.21 by 15.01 inch box. But I wouldn't suggest relying on that. And then, as I said, you get 3 Vs, which is kind of 3 times $1,500 basically per violation, and then every 0.1 inch extra. So if you had a frame member that was 0.21 by 0.2 by 15 inches, you're going to get 3 Vs. If you had a frame member that's 0.3 by 0.2 by 15, you'd get the additional 2 Vs, and so on for every 0.1 inch extra. Wall members are similar idea, but these ones are kind of those thin rectangular pieces we'll see in a second. These ones have to fit in 0.1 by 3 by 11 inch box, so you can see they're thin and much wider and taller. They have to be at least 1.5 inch tall and at least 1 inch wide. I hope most of you remember about wood is that wood has a certain grain, and in this case the grain has to be oriented vertically. And again, they give you a tolerance of 0.01, and you get 3 Vs per violation, and an additional 3 Vs for every 0.1 inches extra. And you can see what I mean by the boxes. So they're not going to they don't have a box where they cut your member out and check it. They're just going to measure this with calipers or with rulers. So your frame members have to fit in this 15 by 0.2 by 0.2 box. They can't be smaller than 0.09 by 0.09. This is what your wall members can fit in, 11 by 3 by 0.1, and then you need that grain to be vertical, which is what those lines are intended to show, and then it has to be at least 1.5 inches tall. Connections are really important, so if any 2 members are touching, they have to be glued, even if they're off by like a little bit. I think what they usually do is they'll take a piece of paper and run it through, and if it's like that they can see that piece of paper separates those members, then you're going to get this violation. They should be glued. Any member touching the roof or base plate has to be glued to it. Those FABI surfaces, which just means where 2 members touch, cannot exceed 1 inch from the centroid of that surface, which just means the biggest connection you can have between 2 members is 2 inches, essentially. So if you imagine you were going to glue, 2 members side by side, the biggest like one of those members can't be more than 2 inches. Otherwise, you're going to have your fairing surface larger than that. And you can't like just glue parts of it because, you know, if they're touching, they have to be glued. There's also what's called excess glue. So if you have glue more than 0.5 inches from the centroid of the fairing surface, which means that you shouldn't just like slather glue all over your tower. You should be kind of precise where you're applying it. And then if you violate any of these, it's 3 Vs per. So I think some of you are familiar with this picture. This is the U of T tower from 2016. Pretty picture. We use it a lot. You notice that those architectural pieces on the outside are curved. We had a ton of violations that year where, you know, they're barely touching these braces, but we didn't think they should be connected, so we didn't think to glue them. And it would happen like all throughout the tower. I think it ended up being almost $100,000 in violations, which was the difference, I think, between 6th and 8th or something like that. So yeah, watch out for that. These ones are easy to kind of screw up, and they're easy to screw up a lot over and over, where you accumulate these violations everywhere. So these are from the design guide, some pictures to help you understand. So this is 2 members glued butt end. So this one's just cut flat and attached to that one. And you can see that's the fairing surface on that member, and that's the fairing surface on that member. And then if you notch your member like this, so if you cut a little hole so that you have increased surface area, so you have increased surface area, then you can see what's shaded as the fairing surface inside and then on the outside. And then in this case, you know, they tell you there's 3 surfaces. So there's 1, 2, 3 surfaces on this member, and then 1, 2, 3 surfaces on that member. This is what they're talking about excess glue. So you can see the connection is just where the brace is coming into the beam or column or whatever this is. If you were to just slather this in glue, like the lightly shaded area, it has to be within 0.5 inches from the center of that fairing surface. If it's past that, you get dinked with a couple of violations. Gusset plates, so those kind of diamonds that you see connecting the braces and the beams, those are called gusset plates. They can't be in contact with walls, which are those like thin, long members, but they have to be touching at least 2 frame members, so it can't just be on only 1 frame member. They have to fit in an inch by 0.1 inch box, and then any violation of this is 3 Vs. Notice there is no tolerance for this, so if it's 1.01 inches by 1 by 0.1, it's a violation. It doesn't matter. There's no tolerance. Actually, we got, I think, a couple of violations for this past year where it was like 1.02 or something, or like really close. And then I think University of Victoria had it even closer where it was like in the 100th of inches, and they were like, no tolerance, you get the violations. So yeah, be really careful. I'd recommend not cutting it to be close to 1 by 1, but like 0.9 by 0.9 or using a laser cutter so that they're consistent. The point of these is to make sure that, you know, members don't come apart. So in this case, it's making sure that this brace, all the forces going into that one, and they don't come apart in shear. Dead load, so this is what adds weight to the tower. We'll have a good picture of them in a second. They're added prior to the testing. You need connections, so you can't just kind of put the dead load on a beam. It has to be firmly fixed. To the tower. And usually teams will have either a hole in a gusset plate or some kind of V so that when you screw it in, it's not going to move around. And you'll see it's going to be a really bad thing if they move around, both structurally, because then things are going to clang around and probably wreck your tower, but also you might have your tower count as collapsed if you can move it, which is bad. The bottom of the rod rests on the top of what's called the perimeter beam, which we'll talk about in a bit. And we have those rods on every other floor, starting at floor 5. You have an 8-minute time limit when installing them, which is usually not an issue. I think last year we had 3 or 4 minutes to spare. It doesn't take that long. And any violation here is 5 Vs. So, you know, 5 times $1,500. So you can see here what we're talking about. It's the rod going through the tower. So this is an example for the L part of the tower on floor 5. If it's shaking this way, the rod is going to be put in this way. And you can see what it looks like here. It's just a stainless steel threaded rod that they put in. You have a washer and nut, 2, you know, steel plates, a washer and a nut that's put really tight against the tower so it can't move. And then it'd be the same thing on the square. You would have it just centered along the plane dimension. All right, so for floors, so there's a minimum amount of floors, 13. There's a maximum amount, 19. You kind of want to aim for 19. You get revenue based on your floor area per floor, and the top floors get the most amount of revenue, so you can't really max out your revenue unless you go for at least 18 or 19 floors. Obviously, the taller your tower, the less stable it is, and kind of the stronger it has to be, and also the more it will weigh. But your revenue scales up much more than your building cost or your seismic cost. So it's usually pretty worth it if you're sure that your tower can survive to build as high as you can. The elevations of the floor, which is defined by the top of the perimeter beam, starts at 6 inches. So the first floor is kind of double height, and then it's every 3 inches after that. So 6, 9, 12, 15, so on. And then notice not every floor has a weight on it. So for example, we can build, you can have a floor 6, but it's not going to have a weight on it, but you can still build a floor there for revenue reasons. You're only allowed one independent floor per elevation, which you'll see why that's important in a second, based on the the rentable floor area requirements. And if you have more than one, then they take the biggest one. And any violation of this is 5 Vs. The definition of a floor is a continuous set of perimeter beams, which just means beams that define the outside of that floor. They can be interrupted as long as there's a beam going in and out of that interruption. So for example, if you have a column and you have a beam going in and out of that column, that's fine. You have interior floor beams, which are flush with the top of the perimeter beams, which help you define your floor area. They have to be flat and level, and it's checked with a bubble level, which you can see on the right. It's considered level as long as the bubble isn't entirely outside of those 2 marks in the middle on each side. So even if your bubble is like halfway out of the 2 lines, it's fine, as long as it's not completely out. You also have the lobby floor, which is drawn onto your base plate and just based on your second floor. And then each floor needs a minimum of 36 square inches of rentable floor area. You'll notice there's no violations. That's because if the floor doesn't fulfill these definitions, you just lose that revenue, and that's kind of penalty enough. And you really don't want to lose revenue. That's bad. All right, so when I was talking about rentable floor area, this is what I mean. It has to be within those continuous perimeter beams, which we define. You have interior floor beams, so these can be structural or architectural. And if the span between them, the maximum and minimum perpendicular span, I should have mentioned that, this is referring to perpendicular distance, has to be more than 0.5 inches, but less than 2.5. Your maximum total rentable floor area for the whole building, summed up, is 2,000 square inches. You need a minimum height clearance from one floor to the next of at least 2.25 inches. Every area of the floor has to be accessible to all other floor areas with using 2 access points. And this is, a big annoying rule that gets overlooked a lot. It cost us like $86,000 worth of revenue in 2019. I think it cost some teams some revenue this year as well. But basically what that means is, so if you have any kind of braces going through the middle of your tower, you need to make sure that you can get from one side of your tower to the other always with these doors that are 1 inch and 2.25 inches. So if you have, floor area that's cantilevered out of your main building, you need at least 2 of these doors. This also includes the lobby. So on the lobby floor, you need these doors to get out and in out of the building. So this is what I was referring to with the floor. So on the left, we have an elevation view, and you can see, you have a floor 1, which is a lobby, floor 2, 3, 4, and then not every floor has a weight. So you see floor 5 has a weight, floor 7, and then 19 has a weight. We have the roof on top, which is not a floor, and a roof plate. Then we have this base plate on the bottom. And then on the right, this is kind of a better explanation of that rentable floor area. So they took a bunch of distances perpendicular to various members. So notice they're not taking the distance, not perpendicular. They're not taking the distance from here to here because that's not perpendicular to anything. So they took, for example, this distance perpendicular to this member, farthest distances to here, that's greater than 2.5 inches, so this doesn't count as floor area. If they had this number much closer and it was less than 0.5 inches away, that part wouldn't count. And so you can see these 3 shaded squares are not considered rentable floor area because they don't pass the definitions. And what that means is there's 2 independent floor areas on this floor. There's this one on the top and then this one on the bottom right. So what they'll do is they'll count this one as your rentable floor area, and you basically won't get anything from this because it's not connected to this in any way. You can't get from this one to the other one. There's also maximum floor plans, which I was referring to before. So for example, last year we had this L shape on the bottom floors and then the square on top. They have to fit within those definitions, and they measure this by putting kind of a template over your tower. They have a little bit of a tolerance, 1/16, and you get 5 Vs whenever you're greater than this. Char asks, I'm not sure why something does not pass as rentable floor area. Sure, I think I'll go over that right now. So the big rule here is the spans between the interior floor beams has to be greater than 1/2 inch and less than 2.5 inches. So all the pieces here that we see are our floor beams, whether there's these thick structural ones or these thin architectural ones. So they measured the span perpendicular to any of these members. So for example, they look at the edge of this member and they measured the largest distance perpendicular to it, so to this point. This is 1.89 inches, which is greater than 0.5 and less than 2.5, so it's fine. When you look at the span, for example, from the edge of this member, the maximum perpendicular distance looks to here, and that's 3.88 inches, which is greater than 2.5 inches, so that part does not count as rentable floor area. Same for this one, same for this one. The other rule was that every area of the floor has to be accessible to all other areas with 2 access points. But you can see there's no way to get from this area to this area. You can't cross kind of through the column. You have to cross either through here, which is not floor area, or here, which is not floor area. And the other rule is that there can only be one, individual floor area per floor. So since there's this top one and it's not connected to this bottom one, this one doesn't count for any floor area calculations, only the top. Okay, so for the base plate, so the tower isn't just like put on top of the shake table. You have to put it on what's called the base plate. Actually, Grace, I think I'll address your question in this slide. So this base plate is 18 by 18 inches, made of either plywood or MDF, although kind of the pros and cons, MDF is flat and kind of easy to cut, but much heavier than plywood. So those are kind of your, what you have to deal with. It has to be centered on, the model itself has to be centered on the base plate and no closer than 1.25 inches from the outer edge. And the reason for that is they use these C channels to clamp it down to the shake table. So if your model's in the way of these C channels, they can't attach it to the shake table and you won't shake. They have a tolerance of 0.25 inches on this measurement. And if it's like 8.5 inches by 18 inches, you are disqualified, which, yeah, be careful with that. And then it has to be between 0.25 and 0.5 inches thick. You're allowed to do notching, which I'll talk about in one sec, but it's just basically these holes that you can make. The bottom has to be flat and smooth, and you need a second identical base plate to bring to the competition to weigh your tower. Because what they're going to do is they're going to weigh your tower, and then they're going to tear off your, they're going to like TARE, tear. So they measure the weight of your base plate and your roof plate, and then they take that weight off of the weight of your tower to get the weight of kind of like your actual balsa wood building. So notching, so it would kind of be not advisable to just put a member onto the base plate and just glue them on. So what teams usually do is they'll cut a little bit into the base plate, they'll put the member in, and then they'll fill that hole with glue. And there's a couple of rules about this. So the notch has to be filled in with members or glue, and there can't be glue present past 0.25 inch of the edge of the member. So this one on the bottom left, that's fine. It's fully filled in with glue and it's not past 1/4 inch. This one is not fine, so you have glue past 1/4 inch from the edge of the member. So that's 5 Vs. And then these two are not fine because their glue is past, 0.25 inches of the edge of a member. It's not near any member. So those are both 5. So this one is 5 Vs, and then I believe this one is 10 Vs because you can see it is not filled to the top with glue. So Grace is asking, can you explain more about bubbles in the base plate glue? So I believe, Grace, correct me if I'm wrong, but you're referring to some violations that U of T got last year. So U of T uses wood glue for our base plate, and wood glue, as it sets, sometimes you get bubbles in the glue. What's wrong with that is if you have a bubble that forms kind of at the very top and you don't fill it in with glue, it's going to be considered not fully filled in. So even though initially you filled it in completely and just as it's set, it happened to create that bubble, you have to go back and fill that bubble in with glue. Otherwise, it's going to be considered not fully filled in. And that's why we got those violations this year. So the roof plate, so just like we have the base plate on top, we have the roof plate on the bottom. And sorry, let me restart that. So just like we have the base plate on the bottom, we have the roof plate on top. It's 6 by 6 inches. The purpose of it is to attach the accelerometer on top so that we can measure kind of our acceleration and displacement at the top, which we use for our structural calculations. You can see here it has a thickness requirement. Highly recommend to use 3/8. We had a big issue this year where we used like I forget what we used. I think we used like 7/32 because it was a little bit thinner, and so our tower would be a little bit lighter, which is cool. But what ended up happening is we forgot our second identical roof plate in my hole in Toronto, and America does not sell 7/32 plywood in San Diego apparently, and so we had to like tear off our existing roof plate, like rebuild. We'll go to Home Depot, buy 3/8 wood, cut 2 new roof plates, and install it, and that was a big hassle that I wish never happened, and was the most amount of stress I've had in a long time. So use 3/8 because in case anything happens, it's widely available everywhere. If this one, you can notice 20 V's, a lot of V's. So yeah, don't be less than or greater than 0.3 and 0.4. Has to be centered on the base plate. Same thing as the base plate. You can notch it, but it has to be filled in with members or glue. You need the top to be flat and smooth, and you need that second identical roof plate for weighing. Weight, so the weight of your tower, everything included, base plate, roof plate, damping devices, cannot exceed 5 pounds. If it's greater than 5 pounds, you are disqualified. I think you might still shake depending on how far above, but this is, I think, one of the most common ways teams are fully disqualified. Weigh your tower before shipping it. Do not do all this work just to get disqualified from this rule. Super important. You know, we decided to use thinner plywood this year for our base plate because we were worried that if we used the 1/4 inch plywood that we normally use, we would get disqualified for weight. So yeah, big consideration. If you build a test tower, weigh it just to see how your regular tower is doing. Before you ship your tower, weigh it with a scale so that, you know, oh no, if we're at 5.5 pounds, we're going to have to, you know, take something off, because it's better to shake and have your tower, at least, you know, it's better to get 25th than disqualified, even if you have to take a bunch of stuff off. Ground motions, so you get 2 ground motions, GM1 and GM2. You get them ahead of time. You get the accelerations as well as the spectra, which I covered in our first tutorial. And then this section also details the dead loads, which floors are installed on. So sorry, this is a mistake. They're not installed at every floor. They're installed at every floor specified. So 5, 7, 9, so on. The top floor, which is just, you know, if your tower is only 15 floors, then the top floor is the 15th floor, but usually it's the 19th floor. Has slightly more weight, 2.69 pounds, and it's 1.96 pounds on every other floor that has a weight. And then you have your accelerometer on top, which is about 0.85 pounds. Penalties and collapse. So quick definition, an unsecured floor dead load is any of those rods if they can move more than 0.5 inches from their original location, or if they can be moved more than 0.5 inches. So literally after each shake, you can see if you go back into a video of this, but they'll go through and try moving each rod and see if they can move them more than 1/2 inch easily. Like not by breaking your tower, but just if it's wobbly. So given that, structure is considered collapse if 50% or more of the floors are not level based on the same definition as before. So they'll check with a bubble level on every floor. If 50% or more of the frame or wall members attached to the base plate are separate from the base plate or structural model, 50% or more of those dead loads are unsecured, or if the structural base plate has delaminated to the point where the model is rocking on the shake table, which means your structure has completely come out of the base plate, or the base plate has like split in half, basically, which is pretty sick. I've never seen that one. So this is one of the, I've never seen the structural base plate delaminated, sorry, but one of the most common ways structures collapse is all of the members rip out of the base plate and it's just rocking, or it just, you know, tips over without ever having really shook, which is really sad. 7 is about the score sheets and how you can appeal and stuff like that. I'm not going to get into that, but basically at the end of the competition, they send you your score sheet, which is just a summary of your score. So this is our score sheet from last year. You can see we got some violations, big sad. You can see the weight of our building is the weight minus the base plate weight minus roof place weight. I'm going to go over more with this in the FABI tutorial in a second. Are we always given 2 ground motions, or is there a surprise ground motion test? So we know ahead of time all the ground motions they're going to give us. They don't surprise us. There hasn't always been 2 ground motions. So I think 2019 was the first year we had only 2 ground motions, and then 2017 and 2018 we had 3 ground motions, but they kind of combined I think they just took out the second one and combined the second and the third one to make a bigger ground motion. But we always know what we're going to get ahead of time. I don't think they would ever surprise us like that. I don't know if that's in the spirit of the competition. But yeah, I mean, they can give us as many ground motions as they want. It's just been 2 for the past couple of years. Yes, okay, cool. Okay, so this is the FABI calculator that I made a while ago. And we're just going to go through it quickly. It's not that long, and then that'll be it for this part of the presentation. So you need your structure's weight. So I'm just going to put in, 1.5 pounds, which is similar to what our target was last year. Building footprint is just the maximum dimensions of the tower. So this year it was 12 by 12, which is 144 inches squared. Design life is just something they tell us, it's 100. We have construction cost, which you can see is 2 million times the weight squared plus 6 million. You have your land cost, which is 35,000 times your building footprint. Damper cost, this one's a little complicated. So if you don't have any dampers, it's 0. If you have 1 damper, it's a percentage based on your construction cost. And then it keeps going up, but it caps out at 10 dampers. So once I go to 8, 9, 10, if I go past 10, you can see it's the same, it just caps out. You can see the difference between not using dampers. So our building cost was 155,000, and using a ton of dampers is $10,000, $11,000. So they don't actually punish you that much. Violation. So as I said, you'll see this goes up by 1,500 every single time I add a violation with a flat cost. And then your annual building cost is just these 4 scores added up and divided by your design life. So divided by 100. So that's how your building cost works. So you can see, changes in building footprint. If it goes from 155,000, if I make it 100 square inches, changes by 15,000, which is not that much. You can kind of keep track of our FABI over here. The reason it's negative is I haven't put any revenue in yet. But you can see it's not changing by that much. What really matters, though, is your weight. So if I go from 1.5 pounds, which was our weight last year, to I think Berkeley's weight was like 0.8 pounds, goes down by 30,000, which is a decent chunk of money. Revenue. So the way revenue works, as I said, is each floor has the minimum amount of square inches and a maximum based on your floor plans. And then the cumulative max of all of these floor areas is 2,000. So if I was just to go through, and the way it works is it's just the area in the floor times the revenue you get per square inch in that floor. So if we just go through and max all the floors that have the largest amount of revenue per square inch, which is what you kind of should be aiming for to maximize your revenue. And then let's just say this is 100. And what does this need to do? So this isn't quite right because we need to get 36 inches. But if you imagine I distribute this floor area among these equally, because they're all the same cost per, they're all the same cost per floor. So these floors in the middle, floors 3 to 9, is where you'd kind of cut out your floor area, and you'd want to max it out almost everywhere else to get maximum revenue. Let's quickly go through what this would look like. So there you go. So this is what an example would be for maximum revenue. $620,000. You can see our FABI is now positive at the top. And all you need to check is none of these are less than 36 inches, none of these are more than 144, and then your sum total is less than $2,000. And then it's just, area times square inches is your revenue. So that's your revenue. Seismic cost is the most complicated one. So we're going to introduce something called equipment cost, which is just a flat $15 million. You have the return period of your earthquake, which is related to how often you expect that earthquake to occur. For us, it's just a number that they give us. You're going to input your maximum acceleration and displacement. So let's say, for example, for ground motion 1, it's 6 millimeters and 11 meters per second squared. And what that's going to mean, so what it's going to do is calculate the drift, which is the proportion of how much your tower moved to the side divided by the height of your tower. So you can see it's our number here divided by 60, which is how many inches is 60 inches tall, divided by 25.4 because there's 25.4 millimeters per inch, and then times 100 to get percent. And then we convert meters per second squared to Gs, which is just divided by 9.81. And then hopefully you guys are familiar with the bell curve, because the way we get these values is you take the cumulative distribution of the bell curve based on values they give you. So they give you the average value, and then the standard deviation, which just indicates how this graph is moving left and right, and also how wide or narrow it is. So you can see this one's a little narrower than this one, and that's just, they give you this graph ahead of time essentially. And then you find your drift percentage and your acceleration. So for us, 0.4% and 1.12 Gs. And what you do is you just go along this graph. So 0.4%, something like here. And that's going to correlate to 0.01 or something for this XDN factor. And then 1.12 Gs correlates to something like here. It's like 0.18. So you can see this factor much higher than this one. It's kind of hard to get to 1% displaced drift unless you have kind of a bad tower, but it's really easy to get to 1 G. So the name of the game is reducing this for this portion. So you get those values based on the graph here. And then what it is it's your displacement based one. So the XDN based on your drift multiplied by your construction cost. And then it's your acceleration based one. So your ADN multiplied that flat $15 million. So you can see that $15 million bigger than this $10 million, and this ADN bigger than your XDN. So your acceleration governs your seismic cost a lot more than your displacement does. So that's what's called your economic loss. And then you divide that by the return period of ground motion 1 to get your economic loss for ground motion 1. Ground motion 2 works a little differently. So I'm not even going to go over what happens if you collapse, because it doesn't matter. You're kind of not in the competition. You're not going to get top 10 anyways. So I didn't even code that in. But if you don't collapse on ground motion 2, they don't measure your acceleration displacement. They just take this XDN and ADN to be 0.5. And they use that for the calculation. But it's the same calculation, so 0.5 times 15 million and 0.5 times construction cost. That's divided by the return period of ground motion 2, 300, to get your economic loss for ground motion 2. Then you add these two up, and you get your annual seismic cost. Finally, you add in, any kind of bonuses you get. So I've set up this little sheet here where you just put in your rank. So let's say we got second in our proposal and first in our analysis, or I think let's just put an actual one. So we got third in analysis, ninth in proposal, and sixth in presentation. So we got 8% APS, 1% proposal, 4% presentation. Cool. All we do with that is our revenue is this revenue number multiplied by 1 plus our bonuses. And you can see, since our revenue is huge, 600,000, these bonuses, every 1% is another $6,000. Yeah. Building cost is just whatever we calculated before, nothing different. And then seismic cost gets discounted by this APS factor. So, this seismic cost is 6 times smaller than our revenue. So our APS has to be 6 times more than any of these bonuses for it to equalize, right? And that's kind of, it's your revenue minus your building cost minus your seismic cost is your FABI, which is the same number over here. But you can see, if I make all of these ranks 0, so we start up with a base FABI of 366,000. We get first in APS, it goes up by $12,000. If we get first in proposal, it goes up by, what is that? Almost like $90,000, right? Which is huge. Like, this is why I think Cluj-Napoca last year got like something crazy, like $500,000 in FABI. They clean swept basically first, second, third for a bunch of these, and it got a crap ton of bonuses. And you can see this matters a lot more than anything else. Like, these bonuses really decide the competition. If I change our weight to be 0.5, if I make this literally 0, like, nice, that added a lot. But it's so much better if you just get, you know, third and third, and it's the same thing. So that's a quick run through of FABI. People at U of T have access to this sheet, so you can play around with it all you want to see what it, experiment with what it means to change revenue, stuff like that. But that's where I'll leave it for now. And other than that, that's kind of it. That's the end of my presentation. So thanks everyone for listening. If you have any further questions, ask them in the chat. You can see all our previous presentations on the link here, seismic.school.ca/#/academy for future recordings and resources. And I hope you have a good day.